think we'll move on then to our panel. As Mikhail noted, we decided this time to add in some non-VRFB presentations and discussions. And so I'm pleased today to let you know that we've got Dimien and TieFast here to join us. And they both put together some presentations for each company, and then we'll open up to a Q&A after both of those. So let me just turn it over first to Brian.
Hi, everybody. First, let me just say thanks to Vanatech and everyone who's here. I'm really excited to present what we've been working on for the last, I guess, year or so. And just to be very clear, we are doing vanadium-based lithium-ion batteries, and we're commercializing those batteries. You can go to the next slide, John.
Hey, Brian. Go ahead.
All right, so yeah, to restart, Dimien is doing a vanadium-based lithium-ion battery. And again, as I said, we're really excited to share what we've been working on and how we think it'll impact the vanadium field going forward beyond just VRFB technologies. You can go to the next slide. So Dimien is a material science company. We have been working and have a team that's well qualified and working on vanadium-based cathode technologies. Our goal is to accelerate the adoption of battery electric vehicles, and we do that with a vanadium-based technology. For a long time, vanadium has been known to work in lithium-ion systems, but unlocking the material as a cathode has always been a challenge for a number of reasons, primarily related to cycle life. And so while it's relatively understood that this is something that could have been done as an ideal cathode, it took a long time for that to be realized until now, when we've been able to produce a material that is proprietary and unlocks vanadium's full potential as a cathode in batteries. You can go to the next slide. So there are a lot of battery technologies that exist, and again, I want to kind of level set the conversation here that we're focusing particularly in the lithium-ion field and not in these others. And they're all important and they all impact our lives, and we're probably using a lot of them right now as we're sitting on laptops, or got in the cars this morning, or even using alkaline batteries. But today we're talking specifically about lithium-ion, and I want to describe a little bit about how those work. And this may be repetition for a number of you, but I think it's important that we all understand what a lithium-ion battery is, how it works, and what the components are that are important to its usage. So John, you can go to the next slide. So there's the positive side. So we're all familiar with alkaline batteries. When you put them in a toy or a remote, you have to put them in the correct way. The positive terminal is actually a ceramic material. It's typically made up of transition metals, and it has a polymer and it has conductive additives in it. Those materials are paired with an anode. This is the negative side of the battery. This is primarily made up of traditionally graphite or carbon-based materials, again, with polymers and conductive additives. When these two things are joined with an electrolyte, you can have lithium ions move from one side to the other, and that either creates a charge or creates a discharge, and you use your battery that way and you cycle it, generating electricity or plugging it in to charge your battery. Next slide. Typically, we see these devices that come in many shapes, many sizes, and many formats. This is the 18650 format, which is just a number that represents how tall and wide the cell is. This technology was the prevailing technology in, for example, Tesla vehicles when they first started. So what's really important, though, is the breakdown of cost in lithium-ion batteries. And so this is a once-in-a-generation opportunity to really impact the energy storage market, which right now is roughly estimated to be about $65 billion. Cathodes, so this is a fully burdened cost for a battery cell, those 18650s you saw. And you can see Bloomberg here pointing out that cathodes make up 51% of the cost of these materials. And so this is a huge impediment to developing new technologies, to making them more market, giving them more market penetration by reducing their cost. And so one of the primary goals of the Department of Energy is to, one, set a target for the full cost of the cell, including the pack, at $75 a kilowatt hour. John, you can go to the next slide. They want to eliminate some of the critical minerals in these technologies, primarily cobalt and to some degree nickel. These are troublesome materials, both from a resource allocation perspective and from a cost perspective. There's going to be a big push in recycling lithium-ion technology, having that readily available and having that capability widespread. And then one of the other large pushes by the Department of Energy is making these technologies capable of fast charge. Fast charging is critical for electric vehicles and giving them the ability to be closer in cost parity and drivability to your internal combustion or gasoline powered vehicle. We can go one forward. So if we look at this from a very holistic perspective, the cathode being the largest cost component, it is the driver of most of the cost in the battery. What can we do at the cathode? Well, first you need things that are materially abundant. So anything greater than 20 parts per million in the Earth's crust. This cathodes have already been used. So we are looking at manganese, iron, cobalt. Again, I put an X through cobalt because it is more expensive and primarily sourced from one region in the DRC, nickel, and then aluminum, and obviously lithium in a lithium-ion battery. Now, when you start going through and thinking, well, what else can we use in the battery? There's not a whole lot of viable options that have both performance, cost, and are widely available in the Earth's crust. And so we have elements like sulfur, which have been used for a long time in lithium-ion, or attempted to be used in lithium-ion and have unfortunately failed. And then there's vanadium. And this is where we think vanadium sits in a very strong position as a lithium-ion cathode material, because it has all of these necessary attributes to fit the widespread market adoption of electric vehicles and other energy-based systems. Go to the next slide. So just a second. So existing cathode technologies require auto OEMs to make some untenable trade-offs. So we have high nickel, which is a dominant technology, very good energy density, but questionable line of sight to cost parity with an internal combustion engine vehicle. And the supply chain is significantly challenged, as all of the low-cost nickel resources have already been exploited. And so as you go and want more nickel, you're having to use higher cost mines and resources that are more difficult to commercialize. Cobalt, again, as I mentioned, is difficult, and that is a component of high nickel. LFP, which is based on iron phosphate, as it sounds, is iron, so it's very, very low cost, but it has a poor energy density. And so while it has a good cycle life and its security of supply, its energy density leaves something to be desired in electric vehicles. And so, we're still looking for the option that makes the most sense. Dimien's V2O5 technology, not to be confused with the V2O5 that is produced commercially, which is the alpha form. Our proprietary V2O5 combines some of the best features of nickel and iron phosphate based cathodes. And it does so giving you a whole suite of advantages and enables a cost-effective pairing of V2O5 with other anode technologies. We're just getting started, and there's several pathways for V2O5 to enter the market. And unlike VRFBs, lithium-ion batteries are ubiquitous to many applications. So this can go from your portable electronic device to an electric vehicle to even some grid level energy storage. Dimien's primary advantage using a vanadium material is that we enable multiple lithium ions per redox center. Let me explain this a little bit. Cathodes are ceramic transition metal oxides, just as V2O5 is. You can think about these as being parking garages for lithium ions. As you know, in a typical lithium ion battery, you park one car per parking spot. Vanadium has the advantage of being able to park more than one car per parking spot, which allows it to store more lithium in the same volume or mass, which is called gravimetric or volumetric energy density. This is really, really important. It means that this material can accommodate a higher energy density in the same space and size, for example, in an electric vehicle. One of the main advantages that we've unlocked is that we've produced a form of vanadium, and we call it Zeta V2O5, that doesn't have any expansion or contraction or phase changes that are typically detrimental to cycle life and capability of a cathode material. So we're able to store more ion, and we're able to do it reversibly without damaging the battery. So Dimien's R&D leads to the production and sale of first cathode active materials. We call this CAM, and then that gets up integrated into electrodes, into cells, and into modules. To be very clear, we start typically with commercially available V2O5. We then do a batch water-based process that lets us create our novel patented polymorph of V2O5. And our business model is to continue to be a cathode active material supplier, and then to produce demonstration and proof of concept cells that we're going to move forward along and up this supply chain. Now, specifically talking about the difference between vanadium, lithium ion, and VRFBs in our example, John, you can skip one forward there. Yep. And so this is kind of where you see a big difference. So in vanadium redox flow batteries, you have a roughly 5.5 kilograms of vanadium per kilowatt hour. And that's a liquid-based system. In a vanadium lithium ion battery, you have substantially less vanadium per kilowatt hour. And you can imagine how this impacts your price of vanadium per kilowatt hour in a vanadium lithium ion battery. And so this is one of the main differences you're gonna run into as you use vanadium lithium ion, which is a benefit to that technology in these lithium ion cell markets, and really is the reason why, as we go back to that beginning slide where you saw 51% of cathode costs are from lithium ion, 51% of the cost of a lithium ion battery are due to the cathode. So being able to use vanadium very effectively and efficiently per kilowatt hour is really important for lithium ion battery because it reduces your cost point. So given the obvious advantages of vanadium in the market, it's widely abundant, it is really efficient in using lithium ion. We've produced a very stable form. Why hasn't vanadium been successful? You know, what's holding it back? Commercially available materials, alpha V2O5 is an unstable form of vanadium electrochemically. It's not unstable in air, it's just unstable electrochemically when cycled. And what ends up happening is that you go through multiple rearrangements of the vanadium ion as you insert more lithium, and some of these become irreversible, which obviously destroys your battery cycle life. Stan Whittingham has been working on vanadium batteries for years. He's part of our team. He's a research collaborator working with us to develop our Zeta V2O5 form, which is extremely stable. And as you insert lithium, the vanadium oxygen framework in our arrangement of VO doesn't change, which allows us to produce batteries that can be cycled many, many, many times and are capable of fast charge discharge cycles. So we have batteries that have charged as fast as 5C, which is about a little under 10 minutes of charge discharge time. Okay, one more. And so to sum up, we're unlocking the potential of vanadium. It's a new cathode material called Zeta V2O5. Again, not to be confused with vanadium flow batteries. That is probably the most common question we get. So the vanadium flow battery story is definitely out there. But vanadium really checks all the boxes, and for the same reasons it does with flow, but different in lithium ion. It's high energy density. It can use many lithiums per site. It has high cycle life. We all know, it's the 5th most abundant transition metal. I want to point out that's 1.5 times higher than nickel and 2 times higher than copper, which are materials that are used in batteries traditionally and commercially. And it's a geographically diverse supply chain, and it has a historically low cost supply price. And again, our team would like to thank you, and feel free to reach out. My email's on the page, and we can talk about this more. Happy to discuss it further. Thanks.
Thank you, Brian. Great presentation.